HSM. This is actually a part of a series of our webinars that we have every week. This webinar, as we said, today is HSM. This is actually part 1 of HSM. And the idea behind this webinar is to get you as familiar as possible with all the options in SolidCAM in general. And today, as we said, we're dealing with HSM, going through the functions and showing you certain options that we have within HSM to help you machine the part exactly the way you need to do it, but by using HSM. One thing should be noted: at the end of the webinar, as usual, you'll be allowed to ask questions. There's a place for asking questions. In order to ask a question, all you have to do is click on Raise Hand, write your question in the question area, and when you finish writing the question, just click on Send at the very end of that, at the very bottom of that line. At the end of the webinar, I'll go through all the questions and answer them to the best of my abilities. Again, all you have to do is click on Raise Hand, write the question down in the area of questions, and when you finish writing the question down, just click on Send. Okay, let's get to the webinar itself. As I said, if you remember correctly from last week we were talking about HSR. HSR is the actual roughing module for HSM, and now we're going to actually dealing with the finish cuts that we use in HSM itself. So first, I'm actually going to start with this simple part that we see on our screen, and what I'd like to do in this part is do a finish cut on these surfaces, going from the top over here all the way down to this surface over there, and that includes this stub shown over here and this area as well. Okay, so we'll start by going into HSM, and as you can see in HSM we have all the technologies listed over here that can be used in HSM. So we'll start with the very first one on top, called constant Z machining. What exactly is constant Z machining? Well, picture yourself a profile operation, a regular profile operation, and going down a certain amount each step, and on each step you have a certain boundary that it has to work on. It works on each boundary just like a regular profile operations. So each operation works only in each step works in X, Y only. When it finishes that step, it goes down to the next step, doing another profile cut on that boundary that it has to work on. That's all it really is. It's very simple, works just like a profile, just on each step as it goes down. It looks at whatever the boundary geometry is on that particular step and then goes further down. Okay. Going into the operation, the geometry does not have to be chosen. It's put in here automatically since I defined my target in the very beginning. So that's put in here automatically. Next, we're going to choose our tool. And always note that the order that we have over here is always the same throughout the program. We'll choose Select, and I'll choose a 10mm bullnose tool with a 1mm radius on the corner of the tool. Now let's go into constraint boundaries. We're going to use the option of create automatically, but as far as how we're going to create automatically, this time we're going to use auto create outer silhouette. If you remember last time, we used the option of auto create box target geometry. If I were to do that and click on show, let's take a top view of the part, and you'll see that we actually created a box around the part. But you'll note that this part in itself has radiuses in the corner. So for this, we have something else called Auto Create Outer Silhouette. By clicking on Auto Create Outer Silhouette, it'll automatically create a boundary according to the shape of the outside of the part. Since the shape of the outside of the part has rounded corners as shown over here, the boundary that was created is exactly rounded corners as well. Okay, so this is the geometry that we'll be using. I'm sorry, that's the boundary that we'll be using. Now let's go into passes. When we go into passes, you'll note every single operation that we have in HSM, they'll all have a wall offset and a floor offset. This allows you to use this operation not only as a finish, but you can also do semi-finish in every single one of our HSM operations. Not only finish, but semi-finish as well by just putting an offset on the wall or floor as shown in the diagram on the side. And always note, you'll always have a diagram on the side showing you exactly what that field does, what that operation does as well. Okay, let's go now into step down. At this point, I'd like to do it, and I'm doing this on purpose now. I'm going to go down every 3 millimeters on the part. No, it's going to step down every 3 millimeters till it gets to where? Z bottom. My Z bottom in this particular case, I'm going to take from this surface over here. Let's leave it exactly the way it is, except for one more thing. If we go back into our, excuse me. Okay, we'll leave it exactly the way it is. I'll show you the next thing in a moment. We'll be talking in a moment about the adaptive step down. I'm going to leave it as none right now. Let's do save and calculate and simulate our part. As you can see, the simulation now is running quicker because it does multi-core simulation with multi-core calculation. Multi-core calculation within each operation, so calculates a lot quicker. Now let's take a look at the simulation, and we'll do it looking at the side view. Note that the tool goes around the part, and every 3 millimeters, exactly the way I had intended it to do, it steps down exactly every 3 millimeters. From here, that looks fine. But if I were to put this at the top view, note as I zoom in, the steps widen as it goes down the part. And that's very simple because since it has to go down exactly every 3 millimeters, to get to the next step, it has to skip over this area to get there. So in other words, you're not really going to get a good finish by working on this surface that way. The way we deal with that is very simple. Let me suppress what I've done over here. And I'll open up the operation that I already created. This is so that we can save time with the calculation. If I were to open up this operation, we did the exact same thing. We have our step down, but this time we have an adaptive step down, and I use the option of automatically insert extra passes. It'll automatically insert the extra passes between steps where it's needed. Now, where exactly will it put it in? Let's first take a look at our minimum step down. What happens is as follows. It's going to go down every 3 millimeters. Now, when it goes down every 3 millimeters, if it goes down and it sees when it reaches that 3 millimeters that there's material left over underneath that tool that is less than 0.2 millimeters, it'll skip over that and go down to the next 3 millimeters. However, if there's more than 0.2 millimeters to the next step, it'll stop over there and do a cut there as well. Now we also have a profile step in. The same thing with the width. Any material left over on the side that's less than this value over here, it'll stop there and cut there as well. By the way, when working in this option, we also have the option of working with scallop as well. Let's run a simulation. And this time, we'll look from the top view. This time you'll see that in the top view, it's working a lot smoother on those surfaces as shown over here. We're going to go down all the way. Note when I look in the side view, you'll note that this area goes down every 3 millimeters. And that's because this surface around the part over here is a straight surface. So what's happening over here is that since it doesn't have anything underneath it, there's absolutely nothing to be taken off with here. It'll jump down to its next 3 millimeter step. So this is actually the way you could control it to work quickly on these surfaces over here, but fine on these surfaces over here. Now, one more note that should be taken as well. If we take a look at this step that we have over here, actually I want to go back to my original operation that I did over here. And again, I just want to run the simulation one more time and take a look what happens by this step. You'll note that when it gets to this area, it goes back and forth between the two steps over there. It doesn't go directly down till the end and then go back down on this end. It gets to this Z level, jumps over to this side, finishes, then it goes down to the next. Now, there are many times when people will say, you know what, I'd prefer working all the way down to the bottom on this stub over here, and then when that's finished, then go over to the next one over here. That could be controlled simply by going into our link area. If we go into our link area, we have here something called maximum stock thickness. If I were to click in that field, you'll note that's what's the maximum distance between two surfaces whereas not to jump over from one to the other. If it's as to jump over, to one to the other, if the value is less than what's written over here, it'll go back and forth between the two surfaces. However, if it's more, it'll first finish with one edge and then go to the next surface. So let's change this now to 1 millimeter instead. Run our simulation after this, save and calculate. And note what happens, now try and slow it down when we get to that area. Note what happens when it gets to the bottom. I stopped it now. You'll see that it's actually continuing down on this surface over here, and then goes over to the next surface, to the next stub as shown over here. Okay, now one more thing I'd like to show you on this part is you'll note that when it machined these areas over here, it did not machine this surface over here, or this surface over here, or even this surface over here. Those surfaces were left untouched. That's because those surfaces are flat surfaces, and that's not something that Constant Z works on. Constant Z works down on the step over here. So the way we would finish that is by using a different operation. I'll just do a quick save and copy, so it'll take us directly to the next operation. And instead of Constant Z machining, we'll use the option of horizontal machining. Horizontal machining, as shown in the diagram over here, is specifically made to work on flat floors. We'll keep the same tool, we'll keep the same constraint boundaries, and in our passes, we'll keep the same depth. What I'd like to do, however, is pick it up a touch above this surface so you can see it actually as it's going down to work on this surface as well. So put it at 1 millimeter and note what happens. We'll do save and calculate and simulate. It works on every one of those surfaces. The top one over here, this over here, this, and this one here as well. But note, when it goes onto those surfaces, it treats each surface as a pocket area. So it's actually going in with a helical movement onto the surface. Well, to deal with that, we remember the tech core areas from HSR? We have it here as well. The tech core areas allows you to come in from the outside when it sees that it's able to come in from the outside, as is in this case over here. Let's run our simulation again. as it finishes the calculation. And when we run our simulation, you'll see now that it's actually coming in each time from the outside. Notice it comes in from the outside over here, finishes and goes over to the next area, always coming in from the outside of that particular surface. Okay, now let's go to our next part I'd like to show you. And I'm specifically using simple parts so it's easy to understand and see exactly what the operation is doing. Okay, in this particular part, what I'd like to do in this part is to actually work on these surfaces over here. Now, we've noted before when I worked with constant Z works very well when you're working on steep areas. Very little you have to do as far as parameters. When you're working on shallow areas, that's where you run into a problem with constant Z. Constant Z is not necessarily meant for shallow areas. For shallow areas, we use the option of linear. If we were to open up our HSM, we'll use the option of linear machining. The tool in this particular case that I like to use will be a ball end mill of 6 millimeters. And if I go into my constraint boundaries, this time I'd like to use a different option of create automatically, what we call auto create silhouette. Because in this particular case, if we look on my part, I don't want it to go into the areas of the holes as well, or these slots over here. I actually want it to jump over those areas. So we're going to use the option of auto create silhouette, where if I were to show you what the boundaries were that were created, it created automatically according to the shape of that particular area, treating these internal silhouette areas as islands where it will not go into those areas. In my passes area, again, note, we have our wall offset and floor offset in case you want to do a semi-finish. And we're going to use step over. Let's use a step over right now of every, say, 3 millimeters, so it goes relatively quickly. By the way, we also have something here called pass extension, where when it gets to the edge, if I want to extend it a little past the edge, how much do I want to extend it by? I can extend it by, let's say, 2 millimeters, for example, and I want it to actually extend itself in a tangential extension to move tangent to the surface that it was working on. Okay, let's do a quick save and calculate and simulate the part. And we'll take a look at the tool path that was created. Now, as you can see in the tool path that's created over here, it's going in straight lines, linear, exactly on all the surface. Let's speed it up a little now. Working nicely on each one of these areas. Perfect. Now, there are two areas that I'd like to take note to in this particular part over here. One is this corner over here. The tool that I used is larger than the radius that we have over here. The radius that I have over here happens to be a 3 millimeter radius on the part. However, I used a tool that was the exact same as the radius over here. So what will happen over here is that you'll get a sharp turn in the corner. Now, technically it's okay, but we all know that if we have a sharp turn in this corner, what actually happens physically on the surface is that sometimes you'll get little marks on the surfaces from the pressure of the tool as it's going up. So what I'd like to have over here is to have a little bit of a radius cut on my tool path over here. To deal with that, if we go back to our geometry area, we have what we call apply fillet. If I were to use the option of apply fillet, the tool would automatically, the program will automatically create a radius a virtual radius, I like to call it, around every single one of these corners according to the tool diameter that I put over here. So say, obviously I want to use a tool diameter that's larger than the tool that I'm using. So if I'm using, say, a 6mm ball end mill, I'm going to write it here, for example, 8mm, giving me a radius of 4mm over there. Let's take a look now at the tool path that was created. And it's calculating now the fillets as well automatically into the part. The fillets itself that's created you won't see because those are just virtual fillets, but you'll see in the tool path exactly what happens. Now when I run my tool path, you'll note that these corners now have a radius on the tool path. So by doing that, you don't have that sharp turn anymore, and these surfaces will be left unharmed at all. The tool will just run up the surfaces as it's continuing in a smooth tool path up on that tool path over there without that sharp turn. Now, the next issue I'd like to address is these surfaces over here. You'll note that when it works in the linear fashion, these surfaces, since it's a sharp turn going up over here, it has a wide step as shown over here on the surface. To deal with that, we can actually deal with that in two different ways. The first way to deal with that is within the linear operation itself. If I were to go back into my passes, we have an option called cross. By using cross, right now the default is none, but by using cross, I can say either before or after my regular linear cuts, I want you to go back and work only on those surfaces perpendicular to the tool path that it created before. Let's take a look at the results that we'll get when it does that. And now it's calculating the tool path on this as well as these areas over here. Excuse me a second. Okay. You'll see it's working first on these surfaces just like it did before. But now when it gets to these surfaces, it did an additional tool path working up and down on those surfaces, creating a much better finish for that surface over there. Now, there's one other option I can use because, you know what, some people will say, you know, I prefer working on this surfaces going back and forth, but a little more, with a little finer steps. So, well, what did we do before? Before we did what we did constant Z. Constant Z, as we said, works very nicely on steep areas, whereas linear works nicer on shallow areas. So what I can do is very simple. If I were to open up my technology field, instead of using linear, we're going to use an option that actually combines constant Z together with linear, as shown over here. When I do that, I'll be using the exact same tool, exact same constraint boundaries, but if I go into my constant Z passes, as you see we have here constant Z and linear passes. If I go into my constant Z passes, again, I'll put my step down at every 3mm so we can actually calculate this relatively quick. But what I'll do now is limit my angle. I'm going to have it work only on surfaces that are between 40 and 90 degrees. So the constant Z in this particular case will not work on this area over here at all. Okay, it'll only work on areas that are between 40 and 90 degrees. We'll go into my link, and just for this operation, I'll just make it bi-directional, so it goes back and forth on the surface. Now we'll go down to our linear passes. In our linear passes, you'll note that in our angle, it automatically changed my angle from 0 to 43, giving a 3-degree overlap between this and the constant Z passes. The moment I put this value in over here, it automatically changes this value according to what I put in here, adding another 3 degrees for overlap purposes. Again, I'll put my step over at every 3 millimeters. Now when I run my simulation, obviously after I do my calculation, and as you can see, it's calculating the part right now. We'll take a look at the toolpath and note that it works first on the constant Z around the part and then linear on the part. That's the other way of doing this. By the way, we have control within the operation whether we want to have the constant Z first or the linear first. But this is how this can also be done. Now, one more option I'd like to go into on this part is the corners. The corners that we created here, remember we used the option of creating a geometry with a radius on it. Now, I still at the end of the day have to create my radius over here, the one that I need. So for that, we're going to do another operation. I'll start a new HSM operation. This time for those corners, I'll use what we call rest machining. As you note in the diagram, it'll work exactly on those corners. Now let's see how this works. I'll go into my tool and I'll choose a smaller end mill. The radius that I have to create over there is a 3 millimeter radius. I'm going to use actually a 4 millimeter ball nose tool, leaving me some room to move around inside the radius itself. I've selected the tool, no problem. Constraint boundaries, keep that the same as last time. And now we have our reference tool. Our reference tool is actually what tells us exactly where we want our rest machining radius to start working. So since I was using a radius of 4 millimeters according to an 8 millimeter end mill, so I can write in here the value of 8. So it'll work according to that 4 millimeter radius. Personally, I like to do a little more than what I wrote over here, say 9 millimeters, to give it a little bit of an overlap between where I was machined already and what I didn't machine. Let's go into our passes, and I'll set my passes at this point at every 0.2 millimeters. Let's run the simulation on the part itself. After, of course, it does the calculation. And note what happens. Let me put this in full view over here. It's actually working on every one of those corners, and note it works in line with each one of those corners. In other words, it works parallel to those radiuses over here. You'll note the even step over as it goes in and out. You'll also even note the overlap, how it overlaps with each other nicely, giving us a nice smooth finish on the part. Now, this, by the way, is probably one of the most powerful tools that we have in HSM for finishing off the corners. This, if you measure your tool correctly on the machine, it'll actually look as if this entire surface, together with this surface over here and the radius, was machined with one tool only. You won't see even any kind of mark between the two operations that you did over here, because this works extremely smoothly on the part itself. Now, let me just go back into the operation. You'll note that over here, we worked parallel to each one of the radiuses over here. Now, there are some people that may say, you know what? These areas steeper, I'd prefer not working parallel, but rather perpendicular to that radius in the way that I'm showing you right now on my screen, going back and forth. So what I can do over there is we can start working on this parameter over here called steep threshold. Right now it's set at 90, and you can note that when it's set that way, it works exactly parallel to all of the edges, not making a difference whether it's shallow or steep. Now, if I were to go back in here, let's go to the opposite end of 0. If I were to work on 0, then each one of these edges, whether it's steep or shallow, will be worked on perpendicular to the curve. However, if I were to use the option of 45, then what will happen is follows. All the shallow areas will be done perpendicular, whereas all the steep areas, will be done parallel, whereas all the steep areas will be done perpendicular. Let's take a look at the simulation very quickly on the part, and we'll see the difference between this edge and these edges over here. We'll wait for obviously we have to wait for the calculation to finish. You'll see that as it gets to this area, it works back and forth, whereas in the rest of the areas, it works perpendicular to the part itself. So let me just zoom in over here. Over here, it's working perpendicular to the steep area over here, whereas in the shallow areas, they're all working perpendicular to the toolpath. Now, one more note about this option. When we have the option working at 45 degrees, we have an option over here of saying, okay, right now it's working in all the areas, whether it be steep or shallow. However, I can go into areas and say, you know what, let's only do the steep areas. When I do only the steep areas, as shown in the diagram over here, it'll only work on these corners over here. Let's run our simulation after it does the calculation of the part. Excuse me. Okay, momentarily it'll finish. And note that it'll work only on the corners itself, only in the steep areas of the part, not touching any of the shallow areas. And that's because I told it to do only steep areas. Obviously, if I say shallow only, it'll only do the shallow areas, but not the steep. But as we did before, we did all, and it did all of the areas, these working perpendicular and these working parallel. Okay, let me open up now one more part. The part that I'm going to open is an actual round part, as shown over here. Okay, now there are two ways I like to, first of all, I like to machine this part without going into these edges, these areas over here. In other words, working only on these surfaces over there. Okay, sorry I accidentally opened the part, not a problem at all. So let's take a look at the way we can do this operation. We'll go into HSM, and we have two operations that I'd like to look at: radial and spiral. If I were to use radial machining, our target is there. Our tool, I'm going to use a 6mm ball end mill. And let's go into our constraint boundaries. In our constraint boundaries, I'd like to do what we call create manually. By creating manually is I'd like to choose, in this particular case, selected faces, as shown over here. I use the option of selected faces, and I'd like to select the faces that I wanted to machine on. So if I go into creating a new boundary, we'll choose our dry faces, and the dry faces are as follows. this surface over here. Let's zoom in. This surface over here. This surface. This surface. This. Oh, let's already add this one and this one. Also this surface and this surface. Just simply click on the surfaces I want to work on. Clicking on this one here, this one over here as well, that one. All of these surfaces are surfaces that I want to work on. You'll note I basically picked every single surface except for these surfaces inside those areas over there. I'll accept it. To make sure I took everything, I can always click on show and it'll show me exactly what was chosen. And I'll accept it. Right now it's just building the boundary around the part. And let's go into our passes. Again, we have a wall offset, floor offset, leaving that at 0. If we have our step over, I'm going to leave my step over. The toolpath that's going to actually create it is in a radial, where it's actually going from the middle out. The distance, the step over distance that I put in here, for example, 2 millimeters, is the actual widest step over on the part as shown over here. Now, next, note the center. The center is relative to the home position. If we take a look at the part itself, you'll note that on purpose, I did not put the home position in the middle part, rather I put it on the corner. The reason why I did that was because I wanted to show you that it automatically goes according to the center of the boundary geometry that it has to work in. So it automatically moves the center towards over here. Now we have our minimum and maximum radius of the part. If I leave it at 0, it'll work exactly to the center. And we have the maximum radius, how far out it will go. What's the radius it will work maximum? This was taken automatically from the part. When I take it automatically from the part, without me even having to tell it what to do, in our link area, we can go either one direction or bidirectional. Let's just do simulate, running the calculation obviously first. And as you take a look at the part itself, you see that it's actually working in radial fashion exactly over that, in those entire surfaces over here, as shown. Now, if I were to, for example, change the area where it's working, in other words, the center, if I were to change the center from here to a different point, just for argument's sake, I'm just going to click on a different point, say over here. Note what happens to the maximum radius. The maximum radius will automatically change, giving it what's the maximum area that it'll work up to. So the maximum area will be all the way out to there. Minimum, obviously, 0 still. Running my calculation and simulation. You'll see that this time it's working off of the center over here that I picked on the part. All the tool paths are actually centered towards this area over here. Going around the part exactly to where it had to get to. Okay, now, just like we have, by the way, if I want to put this back to the center, no problem. I can either pick my center over here, right on the point over there, and that'll work for me as fine, or right click, reset this parameter. That will also do it as well. Now, another option we have by working on this part is working actually spiral on the part itself. If I were to take, instead of radial, right below we have spiral machining, it'll work with a spiral cut on that surface. Same tool, same boundary. The passes, let's do every 2 millimeters, and we'll run our simulation after it does the calculation of the part. Excuse me. Note, this time it's working spiral along the part itself. And there we have it in a spiral type of a toolpath. Okay. I'm going to stop now. Obviously, we'll continue next week with part 2 of HSM. But now, I'll give you a moment or two to write down the questions that you may have. Just a quick reminder also, the webinars that I've done up until now, and this one including as well, this one will be put on by tomorrow afternoon. However, the ones that I've done already, we can find them on our website, so you can always review them as well. If we were to open up our website, you'll see that we have the area of webinars and webinar recordings. By clicking on that, you can see all the webinars that we have over here. And besides viewing them live over here, you can also click here to download the video. If you want to actually download the video itself, you can click on this and you can see and then download it and view it in high definition. Okay, I guess that's it for now. We'll see you again next week when we have our next webinar on HSM Part 2 as we go through the rest of our options in HSM. Everyone take care, have a great day, and of course, have a great weekend as well.